Today my talk is about a real-life implementation of the multi-tenancy feature for Lustre. Let's get started. Here's the outline of the presentation. First, I will re-explain the multi-tenancy concept, and then I will give details about the real-life use case of Uppsala University, so their requirements, the solution we proposed, how we managed to implement it, and of course details on the performance we were able to achieve. So let's begin with the multi-tenancy concept. As we initially designed it, the isolation feature was thought as a combination of three main Lustre features. So we have strong authentication, subdirectory mount, and node map. So it means that we need a strong authentication because we want every Lustre client to authenticate with its own credentials. This is important because we want to make sure that the client's ID is really the one it claims to be. We are using subdirectory mount because we only present a portion of the global namespace to the clients, and it depends on their identity. And we use the node map feature because we want this file set presentation to be automatic. And we are also doing UID-GID mapping. So this isolation feature makes Lustre multi-tenant. It means that we are able to have different populations of users on the same Lustre file system. They would ignore that they are sharing the same file system. They would not be able to even see the data from other populations. And of course, they would not be able to get access to it. So this is the concept as we initially thought and initially designed. But what if strong authentication is not available? I mean, we need to make sure that the client's ID, as seen by the Lustre servers, is the one that they pretend to. And if strong authentication is not available, we have to find another way to control the client's ID. There are several reasons for which we could not use strong authentication. The first one is, for instance, if you have a site where strong authentication is not already in place for users, maybe it's too complicated to start using strong authentication with Lustre. Another reason is if your application's workflow makes use of a heavy use of containers and VMs. Maybe in that case, having to dynamically instantiate the credentials with your compute nodes and then spread those credentials to the corresponding nodes is too complex. And so it's, you do not want to go this hard way. Okay, so let me present to you the Uppsala University. So they are dealing with life science. They are in Sweden, not that far from Stockholm. Their requirements were 4 petabytes usable storage, 24 gigabytes per second read and write. They wanted to support up to 200 tenants and 15 parallel at minimum, and with heterogeneous bandwidth needs. And no strong authentication at this customer site for the two reasons I mentioned before. They have, in their application workflow, they make use of OpenStack. It means they will dynamically instantiate the login and also the compute nodes. And their compute cluster has a 40 gig e-interconnect network. So here is the description of the solution we proposed. This solution is based on Lustre 2.10, so by the time of this project, this was the latest Lustre version available, no 2.11 yet, and moreover, it's more important, it's the latest LTS version available. So for the storage side, we are providing an ES14KX system. It has 4 SSs. We use separated nodes for MDS and MGS, and it's connected on an InfiniBand network. So because we have to provide multi-tenancy, we are using the node map, and we are declaring node maps on this system. At Uppsala, the number of tenants is pretty stable over time, so we will create as many node map entries as they have tenants. And basically, a tenant is made of 5 to 6 users and 2 groups. So we will map directly the UIDs and GIDs of those legitimate users and groups. And in order to be application friendly, we will not use the squash unknown feature on the node map. The deny unknown. We will use the squash feature in order to squash the unknown UIDs and GIDs to a default UID GID for the given tenant. So because we have an InfiniBand network on the storage side and they have an Ethernet network on the compute side, we are proposing to use LNet routers. And we are also proposing to assign a whole LNet network to each tenant. So it means that tenant A will be assigned LNet network TCP 2101, tenant B LNet network TCP 2102, and so forth. So it's pretty simple to configure. One on the node map, one LNet network matches the one tenant. As I said earlier, they are using OpenStack, so it means they are running their applications inside VMs. And in some cases, the users could be root inside the VMs. So you could imagine a malicious user that would modify the LNet configuration on this compute node, also change the LNet routes. And then it means that, for instance, a compute node that is part of tenant A or tenant B could try to modify its configuration so that when it connects to the servers, it is seen as part of LNet network TCP 2103, and then it is considered by the servers as member of tenant C. So in this case, this node would be able to get access to data that it's absolutely not supposed to. Of course, we have to prevent from this. This is a security problem. And in order to do this, we propose to use VLANs and virtual LNet routers. So it means that we on the hosts that are running the client VMs, we make sure that when OpenStack instantiates a VM for a compute node, the interface, the network interface that will be used by this client, by this compute node, will be tagged with a VLAN that corresponds to its tenant. So for instance, for tenant A, we use VLAN 2101, tenant B VLAN 2102, and so forth. And similarly, when we instantiate the compute nodes with OpenStack, we also instantiate virtual machines on dedicated hosts. We call them the KVM host. And we run Lustre routers inside those VMs. And similarly, we tag the network interface used by this virtual router that is dedicated to a tenant. We tag the network interface with the same VLAN. So it means that, let's get back to this malicious user. It will still be possible for him to try to modify the LNet configuration of the compute node. And it will work, but it will be able to change the configuration. But what will not work is that this compute node, this Lustre client, will not be able to connect to the servers. In fact, the connection will be blocked at the underlying network level by this VLAN mechanism, and so it will be blocked by at the LNet router level. So this is how we achieve, this is an example of how to achieve multi-tenancy without strong authentication. Okay, this slide is just here for reference. It's a summary of what I just said. So I said that we are using LNet routing in this project. We are also using multi-rail. The reason is the following. We have 4 OSS servers. Each of them has 2 network interfaces on the InfiniBand network. We have 2 IB switches. And so we decide to connect the first interface of each OSS to the first IB switch and the second to the second IB switch. On the KVM host, the hosts that are running the LNet VMs, LNet router VMs, we have 2 dual port connectix 4 cards. So we configure one of the ports on the EDR network and the other port on the Ethernet network, which means we have 2 interfaces on the InfiniBand network per KVM host. So similarly, we connect the first interface to the first IB switch and the second to the second IB switch. And we configure multi-rail on top of this, LNet multi-rail, which means we only have one LNet network. And it means that in case of failure of one InfiniBand switch, we are still able to reach all the Lustre targets transparently, and similarly, we are still able to reach all the Lustre routers. So I said we have dual port network adapters on the KVM host. And for each one, we have one port configured on the Ethernet network. So that would mean two network interfaces on the Ethernet network. Unfortunately, at the moment, only one is connected to the compute cluster. So we have 6 links going from the routers to all the compute nodes. A few words on some issues we hit while running this LNet multi-rail plus routing configuration. First, we hit a timeout issue. This is related in LU 10707. So basically, this is a timeout issue that occurs when doing routing on a TCP network. And in order to work around this issue, we have set peer timeout to 0. This issue is about to be fixed, so it should be fixed in Lustre 2.10.4. And we also had a small issue to make multi-rail work in this environment. So we are using Lustre 2.10, which means we do not benefit from dynamic peer recovery. So it means that for every peer in the network that is multi-rail capable, we have to run commands in order to declare that the peer is multi-rail capable. And we had to not only declare the remote peers on the local network, but also the remote peers on the network that is beyond the routers, so on the other LNet network. Otherwise, it would not work. Okay, so let's move on and talk about performance. As a reminder, the performance requirement is 24 gigabyte per second, so it means 22.3 gigabytes per second. All numbers here are in gigabytes. And we wanted to see what was the impact of every layer we would add in order to come to the proposed solution. So I will not go and detail every number on this slide, just to mention that here the bottleneck is the number of links we have between the routers and the compute cluster. It's only 6 40 gig links, so it means a maximum of 28 gigabytes per second. And we are happy to reach 26, and it's higher than the requirements. And the other good thing here is that when we activate the node map feature, we do not see any performance penalty. So this is bandwidth, and this is quite interesting. So this is a summary of the performance we get. So now let me get into more details about how we decided to size and how we configured the virtual and net routers. First, we were wondering how many cores to assign to the virtual routers running on the KVM hosts. So we simply tried, and we have varied the number of cores assigned to one router running on one KVM host. As you can see, the read performance is pretty stable. It increases just a little bit. The write performance really depends on the number of cores, and we reached the maximum performance with 8 cores. And it's not displayed here, but with more cores, we stay with the same performance level. So let's take this 8 core virtual router and instantiate several same routers on the different KVM hosts. And as we can see, the performance really scales linearly with the number of parallel instances we have of the routers. So maybe it would mean that it's more important to have several instances running in parallel than having one instance with more cores. So we took the reverse approach. We configured virtual routers with only 2 cores, and we instantiated a number of them on the KVM host. So here on the x-axis, 1 means we have 1 virtual router running per KVM host. So it means 6, because we have 6 KVM hosts, it means 6 virtual routers. 2 means 12 virtual routers. And as you can see, as soon as we have 2 virtual routers per KVM host, we're able to reach the maximum performance. So it confirms the idea that it's more important to have multiple instances running in parallel than a few larger instances. So let's zoom in some details. So with you've seen on the previous slide, with 1 virtual router per KVM host, we're able to achieve 16 gigabytes per second in write. So it's 2 core virtual routers. So it means we are using 12 cores on the total of the KVM host. So let's see how many virtual routers with 8 cores we would need to reach the same write performance. So the answer, this is just an extract from the previous slides. The answer is we had to launch 4 virtual routers with 8 cores in parallel to achieve 16 gigabytes per second in write. So it means we are using 32 cores instead of 12. And moreover, as you can see, the read performance is significantly below. So the conclusion is that it's much more important to have multiple instances running in parallel in this context, and it makes sense because it means we are able to process more requests in parallel, and this is how we are able to achieve the best performance here. At Uppsala, they do not have requirements regarding metadata performance. Still, we wanted to make sure and validate our 2 core virtual and net router model. So again, as you can see, the bottleneck is the virtual is the routing layer. It makes sense because when we do routing, we are adding latency on the I/O path, and so of course it hurts metadata performance. But the good news is, when in this, at least in this context, when we activate the node map feature, we do not suffer from any performance penalty. So again, this is good news. In the end, our choice was to only use 2 core virtual routers. easier to administrate, it's more flexible, and it will let us support more tenants in parallel. So we have 6 KVM hosts, I already said that. They have 28 cores each, so we dedicate 2 cores for the hypervisor, which means 13 dual core ALNet routers instances per KVM host, so 78 in parallel. And depending on the bandwidth needs for each application, each tenant, we decide to assign one or several virtual routers in order to provide the necessary bandwidth. But it's also nice because it gives us control on the bandwidths that can be used by a given application or tenant. So as a conclusion, we were happy to see that it is possible to implement the multi-tenancy feature without strong authentication, but thanks to VLANs and virtual ALNet routers, and of course with the unavoidable subdirectory mount, node map, and UID-GID mapping features. We are quite happy with the new technologies employed in this project. So as I said, we are using Lustre 2.10 LTS version, which is pretty stable. We are using multi-rail as well, which works fine. We are also happy with the previously released technologies I wanted to mention, so ALNet routers, subdirectory mount, UID-GID mapping, subdirectory mount. And final word, in the future we want to also implement project quota at this customer site. The reason is that it would even increase the isolation between the tenants, because with project quota we will be able to guarantee a given storage space to each tenant, and so they would really think that they are the only users on the system. Thank you.
Questions for Sebastien?
Thanks. Looks very interesting. Did you do anything about quality of service between the different? Does everybody get like a fair share of the bandwidth? And then also, I was wondering about was there any IOPS requirements or targets to hit as well?
What was the question?
It's for quality of service between all the different tenants. Is it everybody going to get the same? Is it like it'll be equal, or can people get like I want a guaranteed amount of the bandwidth or?
The virtual routers are the bottleneck. Simply by controlling how many virtual routers each application is using, we can control. So we do not instantiate the virtual routers when every job is launched. We instantiate a bunch of them, and so they are already available for some tenants. And if we have needs for more bandwidth or for more tenants in parallel, then we are able to kill some of them and start new ones.
Then, did you also look at IOPS as far as the on the requirements at all, or is there any expectation to that? Yeah.
IOPS side, yeah.
Any other questions? I had one question then. So with the VLAN isolation, that was being applied at the switch. So each virtual instance could only talk on that one VLAN?
We are not really doing it at the switch. A VLAN tag, and on the router side we do the same, but so we could have used OpenSFS, which is a technology where you can assign, you can dynamically create your network interfaces and assign VLAN tags. It was not the case here, just for the sake of simplicity.
Okay, thank you.